So my homework was that to show that the secant z is tangent to z, secant z. So I'm not going to get through all the details. So according to the previous class, we have secant z is written by cosine square x plus sine hypersquare y, cosine x, cosine hyperbolic y, I sine x, sine hyperbolic y, right? And I spent about almost an hour to calculate the partial x partial u and the partial x partial v, right? It has been a long derivation, long calculations, and could be my favorite, like a problem set for the next quiz, which I'm thinking about either end of October or first week of November. So I haven't decided which week for the second quiz. Probably the earlier better for you because the less amount of material you have to study. If you have one more week, then you have one more week amount more worth of class materials to cover. So let's just go back to our previous class and then just use the result. So we obtained partial x, partial u, I'll just simply write down the result. Cosine square x plus sine hyperbolic square y and square sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y partial y partial v, sorry, it has to be partial x. Cosine square x plus sine hyperbolic square y square cosine x sine hyperbolic y sine square x cosine square y. So the secant z is partial x partial u plus I partial x partial v, and I'm getting lazy, so because we have this denominator here up here very often, I just write it down as some function of dz. So let's say d of z is cosine square x plus sine hyperbolic square y. Then we have 1 over d square z sine hyperbolic, we have to be careful too, sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y plus I cosine x sine hyperbolic y sine square x plus cosine hyperbolic square y. On the other hand, Probably you need time to copy. See? There. So if you compare with this, so one of the d squared z is common, and the real part we have sine x cosine x over y as a common factor with the parenthesis cosine squared x minus sine x squared y. Let's just check the real part, compare the real part together, right? Cosine sine and sine x squared plus cosine x squared y. So these two factors are together, same, right? So we can safely say that, okay, so I will, usually this mark disappears and okay, just wait. Tangent z. Also, you have to check your previous note. Cosine square x plus sine hyperbole square y, sine x, cosine x, I, sine hyperbole square y, cosine hyperbole square y. Secant z. So basically this is dz. So I just put dz cosine x cosine hyperbolic y plus I sine x sine hyperbolic y. So secant z tangent z is d square, and for the real part we multiply this with this and subtract the multiplication of this term and this term, right? But that's the real part. So sine x cosine x cosine square x cosine hyperbolic y minus sine x sine hyperbolic square y cosine hyperbolic square y plus d square z. We have an imaginary part. It's cross multiplication. So sine square x cosine x sine hyperbolic square y plus cosine x cosine hyperbolic square y sine hyperbolic square y. So we can put them together as 1 over d square z, and the common factor is sine x and cosine hyperbolic y. And cosine square x minus sine hyperbolic square y plus I cosine x sine hyperbolic y and sine x square plus cosine hyperbolic square y. So that's your secant z times. So let's compare with these two terms together. This and the sine x sine x cosine hyperscale y minus cosine square x minus sine hyperscale y, right? So real part is the same, and imaginary part, common factor is cosine x sine hyperbolic y, and sine x square plus cosine hyperscale y. Let's compare with this. Therefore, you can say dz d secant z is tangent z secant z. The result is same for the real cases, right? So it turns out that the extension to the complex domain, the basic functional result is the same as the real cases. That's an amazing thing. So, because I have done how to do the homework, maybe I will give extra homework. So, check for CSCZ cosecant Z, secant hyper Z, cosecant hyper Z, tangent Z, tangent hyperbolic Z. And find the derivative. I think each of the function will take you about 1 hour to show everything. So 1, 2, 3, 4, 5, 6 hours. So maybe you can spend your weekend doing some homework. And weather is getting cold, so you have nowhere to go anyway. So you can stay either at home or dormitory and do some homework for fun. Maybe you can even watch Netflix while doing homework. So any questions? So far, we have studied the Cauchy-Riemann condition. But sometimes the functional relationship can be expressed as r and theta in polar coordinate. So what would be the cases? So extension, now topic is extension of Cauchy Riemann condition to polar coordinate. Right, for Z I sine theta. So that means f z is usually xy free xy, but sometimes it can be expressed as r theta theta xy. Why this is not disappear? Extend screen in mirror mode. Switch to second screen mode. Very persistence is not going to disappear. It's somehow bothering me. So C, X, Y R theta. So R is square root of 1/2 theta is tangent inverse y over x, right? Or tangent theta is defined as y over x. So U R theta phi. Sorry. If U can be expressed as R x y theta x y, then partial x partial U is something like this. Delta x goes to 0. Delta x U Rx plus delta x y theta x plus delta x y minus U R x y theta x y, right? So it looks a little bit complicated, and when things is getting complicated, what do? You just simply do nothing. That is either add 0 or multiply by 1. So I decided to put add 0. So you can change this into something like this. Minus U R x y theta x plus delta x y plus delta x. So you subtracted this, right? So you just add them together here. So this is actually R plus delta R. And this is theta plus delta theta. So what you can do is you can divide by delta theta and multiply delta R. R and delta R. also divided by delta theta and multiplied by delta theta. Then what you get is simply partial r, partial u, partial x, partial r, partial theta, partial u, partial x, partial theta. It's called chain rule. So you can do basically the same thing for other variables. So have time to copy this. Likewise, delta y, delta u is delta r, delta u, delta y, delta r, delta theta, delta u, delta y, delta theta. And same for the v. Partial r, partial u, partial x, partial r, partial theta, partial u, partial y, partial theta, partial y, partial v, partial r, partial u, partial y, partial r, partial theta, partial v. Partial y, partial theta. So what we need to do is actually, we know how to differentiate with respect to r, so we need to find partial r, partial x, partial r, partial y, partial y, partial x, partial theta, partial y, partial theta, right? And actually, we have already done that, the derivative with respect to r. In the vector analysis, we have done this, right? So partial x, partial r is what? Simply x over r. Or if you check that this is a g, so partial x, partial r is dg d g half, and partial x, partial g. And square root of g is 1/2 over square root of g, right? And 2x. G. Square root of g is simply r over x, right? And r over x is actually, this is r, theta. R over x is cosine theta. We have some small spot. Likewise, partial y, partial r is y over r is sine theta, right? This is your y. This is your x. So in summary, for this part, partial x, partial r is simply cosine theta. Partial y, partial r is simply sine theta. Tangent, inverse tangent function, arctangent is a bit more complicated. Say if h is tangent inverse t, t is tangent inverse, right? So dh dt, so what happens if you differentiate tangent x? Remember the formula? 1 plus tangent square h, right? 1 plus t square. So dt dh is actually 1 over dh dt is 1 over 1 plus t square. So dt d tangent inverse t is actually 1 plus t square. Probably you have this covered in your freshman calculus, right? Or maybe even in high school. No high school? But already you're familiar with how to differentiate with the inverse function, inverse trigonometry functions. So theta is tangent inverse y over x. So let's say t is y over x. Then partial x partial theta is dt d theta partial x partial t is 1 over t square minus x square over y. Let me check. Is 1 plus y over x square times minus x square over y is x square plus y square over y minus 1 over r sine theta. One more thing.
How do you get the sign?
This?
The lower part is R, right?
This one, right? So actually this part is okay, right?
Yes.
And so you can put this as r square y.
Oh.
So it becomes minus 1 over r, y over r, and this becomes sine.
Okay.
Got it?
Yes.
Great. So you can do the same thing for cosine theta. Let me check. Oh, by the way, I made a mistake of writing down tangent square h as a tangent hypersquare h in the previous screen, so I just made the correction. So please check with that. So partial y, partial theta is partial y, partial arctangent y over x. And usually you can say this is t. So this is dt, d tangent inverse t, partial y, partial t is 1 over t square times, this is simply 1 over x. 1 plus y over x squared, 1 over x. It becomes x squared plus y squared over x is r squared over x, 1 over r cosine theta. So if I summarize, someone still copy this note. Oh, what time is it now? Go back. Oh, so partial x partial r is cosine theta. Partial y partial r is sine theta. Partial x partial theta is minus 1 over r sine theta. Partial y partial theta is 1 over r cosine theta. So we can check the Cauchy-Riemann condition. Partial x partial u is simply partial r partial u, partial x partial r, partial theta partial u, partial x partial theta, right? So this is cosine theta partial u partial r minus 1 over r sine theta partial u, right? And partial y partial v is partial r partial v partial x partial r plus partial theta partial v partial, of course, y partial theta. So this is sine theta partial r partial v plus 1 over r cosine theta partial y partial theta. No. Something is missing. Partial theta partial v. So let's compare with this what we'll get. Those two relations are supposed to be the same, right? So cosine theta partial r partial u must be sine theta partial r partial v plus 1 over r cosine theta partial v. Check. So if we combine them together, what do we get? Okay, let's put the cosine factor together. This is cosine, right? So we have cosine theta partial r partial u minus 1 over r partial theta partial v minus sine theta partial r partial v plus 1 over. Oh. Something is very hard. Let me try. Very strange. I'm putting down, but it doesn't show up. Okay. Maybe I'll just move to the next page. So this is the screen that was taught last time. sine theta, partial u, right? So if sine theta together is equal to 0. For all theta. So say if cosine theta A, sine theta B is 0 for all theta. Okay, so we have a algebraic equation that cosine theta A plus sine theta B is 0 for all theta. So what is the condition? For every theta. A is 0, B is 0, right? So the Cauchy-Riemann condition written in polar coordinate says partial r, partial u, 1 over r, partial theta, partial v, and partial r, partial v is minus 1 over r, partial theta, partial u. So this is a Cauchy-Riemann condition in polar coordinate. And maybe I can give you as a homework that partial y partial u is minus partial x partial v. Also give the same condition. In polar coordinate. That can be just, you can do it in 10 minutes as homework. So this is a very neat problem for quiz too. Maybe 20 points. So any questions? So something is odd. So we have, okay, just, oh, screen just stopped, right? If I write it down something, it doesn't show up. Okay, maybe it's an old man that maybe you should take a break, and I'll try to figure it out. This is your attendance list. Please check. For example, we have log z. Theta 2n pi, right? This is your log function. So this is U I V. So U is R, V is theta plus minus 2n pi. So Cauchy-Riemann condition. Partial theta Cauchy-Riemann condition in polar coordinate. Partial R, partial U is what? 1, right? Partial theta, partial V is 1. So partial R, partial U, 1 over R, partial theta, partial V. It's not the same, right? So it's not differentiable in general. On the other hand, if Fz is exponential z, say z, r exponential I theta, r cosine theta, I sine theta, u plus iv. So u is r cosine theta, v is r sine theta. So partial r, partial u is r just cosine theta, right? 1 over r, partial theta, partial v is 1 cosine theta. So they're the same, right? So Cauchy-Riemann condition is satisfied. So that covers pretty much about the differentiation. Now let's cover a new complex integration. So we are following the parallel path from the real variables. So in your middle school days, you learn about functions, and when you get into high school, you learn complex functions like logarithmic, exponential, trigonometric functions, and then you learn differentiation, and then integration, right? And then inverse over differentiation. So we are actually following the same path in the complex domain, and the complex integration is based on two very important theorem. So Cauchy's integral theorem. This is probably the most important theorem that you are learning in this semester. Actually, not the most. You already learned about Stokes theorem, right? Stokes theorem, Gauss theorem. And Stokes theorem is really important because it allows the generation of electricity, right? And Cauchy's integral theorem allows the 18th century mathematicians to do the very complicated integrals, which arises mostly from the Napoleon War. Two things. One is the trajectory of like cannons, and then the calculation of tide for the naval operations. Especially the latter is the most important cases. The domain so when you say domain, it's same as set. So say this is your domain. Means this is a set of complex numbers. And then you have a closed loop. C is a closed curve. When if finite and differentiable. The function is differentiable means they satisfies the Cauchy-Riemann condition. Then we say this function is analytic. So Cauchy's theorem says if Fc is analytic inside of a closed curve C in D, then this integral is always 0. So Cauchy discovered this very important formula in about 200 years ago, something like that. And we are going to see why this is important. But for now, let's focus on the theorem. So Fz is analytic means, number one, Fz is finite everywhere in D, and number two, Fz satisfies Cauchy-Riemann conditions in every point in Z. So let's say F uxy I v xy c dz dx plus I dy. So Fc dz is something like this. Uxy I v xy dx plus I dy uxy dx minus 3xy dy plus I 3xy dx plus u xy dy. You have seen this kind of integral about a month ago, and when we derived the Stokes theorem, that let's say remember this closed line integral, you can convert into this surface integral partial x, partial fy, partial y, partial fx, dx, dy, right? You must be familiar with this. So this is actually something like this, f dl. This is called the Stokes theorem. So, if example set fx as u, fy as minus 3, then u dx minus 3 dy is simply partial x minus 3 minus partial y partial u. And this is 0, right? Because of Cauchy-Riemann condition. We have said FC is on anything is this satisfies Cauchy-Riemann condition. Right? How about the imaginary integral? Imaginary part becomes this 3dx plus u dy. So this is ufx, this is ufy. So again, you can transform into that partial x partial fy u minus partial y partial fx free, right? So this again is 0. Cauchy-Riemann condition. So that means if fg is analytic inside of C in D. So, so let's consider counterexample. When fc is not analytic, what happens? Say and centered at the origin. And so this is your region. Fc is 1 over Z. Can you say that Fc is analytic inside of C? Or let me ask you a different question. Is Fc finite at Z is equal to 0? Finite or not? What happens if we divide something by 0? Infinity, right? So this function 1 over Z may be analytic in most of the place, but not the center. At this point, origin. Fc is not finite at Z is equal to 0, right? It's infinity. And do you think it can be differentiable at Z equal to 0? Again, not, right? And not differentiable. Again, at Z is equal to 0, right? So that means Fz is not analytic. At Z is equal to 0, right? So do you think we can apply that Cauchy's integral theorem or not? No, it doesn't apply, right? We cannot apply Cauchy's integral theorem. So we have to do something else. So on this radius, say Z, you can say R exponential I theta, right? At this point. So dz, R is fixed. So R exponential I theta, I d theta. Z is fixed, R is fixed. So for this integral, you can say theta from 0 to 2 pi, 1 over Z, that is R exponential I theta, R exponential I theta, I d theta. Becomes 2 pi I. So this integral is non-zero, and it's even finite. this is one counterexample of Cauchy's integral theorem. And also this is really important. Now, how about this? Another counterexample, ft 1 over g to the m, and m is integer. And say x, y, r, this is c, theta. So this point C is z, let's say r exponential I theta. dz is r exponential I theta, I d theta. Then the c integral to pi r to the m exponential I m theta r to the exponential I theta d theta is I over r m minus 1 exponential I m minus 1 theta d theta cosine say m is integer. So what is this integral? If you have a cosine something theta over 2 pi. If you have an integer argument of cosine and you integrate it over 2 pi, it's 0, right? Except when m is equal to 1. Cosine theta, cosine 0 is 1, right? So when m is equal to 1, this becomes 1, so this is we have 2 pi. Sine is always 0, right? When m is integer, m minus 1 is integer, you get always 0. So this is very interesting. So this is I 2 pi over 0. Otherwise. So you have very interesting results. Otherwise, it's very odd because the m is greater than 1, still it's not finite and not differentiable with the origin, right? So you cannot definitely apply the Cauchy's integral theorem. Nevertheless, if you do the explicit calculation of this, it's still 0 for some very interesting reason. And this is really important for the later analysis. So what about if it is not circle? Other point, say, C naught, C. This is another counterexample. So far we have done this for the center, but what if it is not at the center? What will happen? This is still R. So this point can be put as C naught plus R exponential I theta, right? So dz is still R exponential I theta, I d theta. So this integral dz still the same. 0 to 2 pi r to the m theta exponential I m theta r exponential I theta I d theta. So the result would be the same as the origin or 0 otherwise. So we have learned that as long as the closed curve is circle with arbitrary radius r, big R, then this integral is either 2 pi I or 0, depending on m. The question is, what about if it is not this circle? So you need a little bit of ingenuity for this.
If it is not a circle, you can integrate it?
Yes, we are hoping that.
Okay.
Very arbitrary. This I'm going to show in the next page. So you are following me, right? As long as curve is circle, you can integrate, right? So question is if it is not. Say something. The question is, so C is not necessarily a circle. So I'm going to cut Okay, so let's modify this smooth the arbitrary function. Slight cut. Make a circle. This is radius of a small row. And say this is C1, C2, C0, C3. And this chasm is epsilon. This is your domain T. So C1 plus C2 plus C0 plus C3 becomes C as epsilon goes to 0. I mean, if epsilon is really, really small, then what happens is, if you need to have a magnifier, if you're watching this part, it will look like this. This is your C2. This is a C3. This is 0. Right? And this is your point. Let me see. C2 is coming down, C2 is coming up. So they are opposite direction, right? So what happened? 0 as epsilon goes to 0, right? C2 and C3 are opposite because C2 and C3 are opposite. And this becomes minus of 0. Because this is clockwise. So if we want to counterclockwise, we have put the minus sign. this whole integral because you are going down and close out, and then z naught is outside of this whole domain, right? So that means we have C1 C2 C3 0 is closed integral, but it doesn't include this point. So it has to be 0. The Cauchy's integral theorem says it's 0, right? Even this is Cauchy's integral 0. But then C2 and C3 are already 0, right? And C1 becomes closed. Minus 0 equal to 0. So this C1 becomes close to C. Easy, right? As epsilon goes to 0. So that means for arbitrary curve, we have this C is basically the same as this. For circle, and it becomes 2 pi I or 0 otherwise. So that means the picture is a bit complicated, right? But it does work for any shape of curve, as long as it's just single path curve. So this is called the Cauchy's integral formula. So why we are doing this? So this is very interesting, right? So the formula, Cauchy's integral formula, actually works for not only for circle, but arbitrary shaped curve. So this result is important because if we represent any function, something like this, So you can generally expand arbitrary function in terms of series. This is called the Laurent series. The important thing is what do you get? Two pi I just B1 this term, right? If C contains C naught. So you have very complicated functions. Very complicated functions, and you have in general a very complicated function, and you want to expand in terms of this Laurent series. And in many cases, if you need an integral, then you don't have to worry about all the other coefficients, just P1. So you only need a single information about this function to calculate the integral. So this is named called the residue. I'm not going to do the calculation, but I'm going to show why this is important. So this is one good example. Let me see. One of the reasons why, because he only needs to find P1 among these all Newtonian force terms. So there's some historical background for you, and why the French mathematicians invented this complex variable theory. And main reason was to do integrals, such as that to find the date for the minimum tidal force happens. So they can expect when the English will try to land their navies, right, their battalions into the French territory. And even though the English was ahead of inventing calculus, they didn't bother because they have a very strong naval force. The French and the English Navy was probably the strongest around that 18th century, 19th century era. So they didn't bother which date is important. They just send enough ships. But French want to be more efficient in their defense. That's one of the reasons why the complex variable becomes important, and main reason was to do integral. So maybe because it's lunchtime, how about stopping here today and continue next week? Sounds great? Okay, bon appetit. Have a nice lunch. (1789) July 14. It's probably one of the most important dates. Anybody remembers that? French Revolution. Let me see. It's called Date de Bastille. Let me check the spelling. Google. date de Bastille. Let me see. Maybe I have to use the French dictionary. Date de Bastille. I used to know the date in spelling, but anyway, it's not important. I think it's a date de Bastille, but I don't remember the spelling. So after the French Revolution, what happened? The English tried to invade France. This is London. This is, I think, somewhere in the Normandy. So the English tried to send their naval ships to the Normandy to land the troops. But in order to land troops, you have to know the tide. The information of tide is very important. And you know that tide is related to the Newton's gravitational law. So you have to calculate the distance, moon, between London and here, R1, R2. The tidal force is proportional to 1 over R12 square. Is R1 square plus R2 square minus 2 R1 R2 cosine theta over 1. And you need to have an average of this because moon is circling around the Earth. So you want to have a minimize the tide by integrating this. Something like this, right? So Napoleon asked Cauchy to calculate when would be the minimum, the date for the minimum of a tidal height. In 1789, after that, 1789. So that's the reason why Cauchy actually invented the theorem. He needed to calculate this integral. And this, I mean, today you can do this very easily, right? Just crunch some numbers in the computer. But in 1789, the French didn't have a computer, right? The only thing they had was a pencil and paper. So Cauchy was forced to calculate the exact date for the minimal tide. happens. So he did invent this Cauchy's integral theorem. And this is actually